Gravando.
Is being recorded.
Okay, good afternoon, everyone. Today is a pleasure to me introduce a friend, João Pedro. João Pedro is from IMPA, is a professor in IMPA. And today we'll talk a little bit about your research. Thank you, João, to accept this invitation. It's a pleasure to us to receive you in our seminar. And you can start, okay?
Okay, thanks, Roberto. It's very nice to be able to talk to you guys. So I must start with a little disclaimer that maybe the focus of this talk, although we're going to have analysis theorems, we're going to have several theorems that have analytic flavor, maybe it is a more philosophical talk. It's not only philosophical talk, I'll be able hopefully to talk a bit about some interesting mathematics to you guys, but maybe use this opportunity to discuss a bit on the future of math, to discuss a bit on the perspectives that we have and related topics. Okay, so the plan of today's talk is we're going to be talking about LLMs. We're going to be talking about lean. I don't know if you guys know what lean is, but if you don't, it's okay. We're going to see a bit about lean. We're going to be seeing about how technology is helping us prove theorems. Technology is improving us, our job as mathematicians, and what the future might hold for us and might not. So let's start with maybe a bit of what LLMs are capable of, what they're incapable of, and what they are known for. I think at this point everybody has fiddled with ChatGPT or Google Gemini or Anthropic's Claude, and it's pretty useful for daily stuff. But also, if you from a year or a year and a half to nowadays, it's actually quite useful for math too. So if you want a quick proof that root 2 is irrational, for 1.5 years, these things are actually able to give you something quite meaningful. So the typical response since the beginning of 2025 of an LLM to the question, is root 2 irrational, is, well, write that in lowest terms, supposing it's rational, then p squared equals 2q squared with p even, so then you reduce everything and you get a contradiction. So it's correct. I tested it. You guys might try it with your favorite LLM, and it's going to spit out something like that. Also, if you go with this slightly more interesting task, if you ask, well, take a connected open set and show that every analytic function with constant modulus is a constant there. This is slightly less trivial. It involves areas of mathematics that we know that some people only see in depth in a graduate course, so some more advanced complex analysis. And for that, you actually have to use the Cauchy-Riemann equations on the modulus of f squared. You have to differentiate, and then you conclude after a bit of hard work that the derivative is 0. But this is exactly what LLMs tell you. So I tried this several times, and actually most of the times the LLMs get exactly this line of idea. So it gets the right track, it gets the idea correctly, right? Okay. So the bottom line of this first slide is, well, it's useful for reminding us how to do stuff. It's useful for these more searching, like literature searching kind of ideas. But then we want to do mathematics, right? So maybe we want to try to go further than that. So let's see maybe why it might be a bit dangerous to rely too much on these. So for instance, if you go and ask, up until some months ago, I think they patched this mistake, but up until months ago, if you ask ChatGPT how many R's are in the word strawberry, it would say confidently that there are 2 letters R. And of course, there are not. There are 3. It just doesn't have a concept of counting, right? We do know what counting is. We know what a letter R is, so we just circle it, and you see there are 3, but it doesn't. It just it predicts the next word in a very sophisticated and fancy way, so it doesn't. In the same way, it also went very viral about a year ago that if you ask ChatGPT 5 what is larger, 9.11 or 9.9, it would say that 9.11 is larger because, 11 is larger than 9. Then 9.11 must be larger than 9.9, which is absurd, but again, it does not have a concept of, well, that's not how larger works for, decimal places, but you see. So you see where I'm going. So there are several other examples, like if you ask whether 91 is prime, it's going to say yes, although it fails to factor 7 out. And if it asks to solve it, like this is a bit older, I think this used to be the case about 2 years ago, that if you asked it to solve x plus 3 equals 7, then it would say that x equals 4 is the answer, which is correct, but then it would say that 4 plus 3 equals 8, and then checks out, which is absurd again, so it's correct, but for the wrong reasons. And this is exactly what we don't want in something that does mathematics, right? So we don't want something that sometimes is wrong, sometimes is correct, but when it's wrong, it has full confidence. This is, at the minimum, very annoying. Like, I think every one of us has had this feeling of being annoyed at people, like you're discussing with someone and they have, they might not be experts at what they're doing, but they act as if they are. And they act with full confidence, so we get a little bit annoyed. We get a bit, we get a bit uncomfortable with that. So you can imagine that with a machine, that's not ideal. That's not how we want machines to help us prove theorems. The problem is that these things are wrong with maximum confidence. So let's see some further examples. I don't know if you guys saw this, but recently there was this whole frenzy online about ChatGPT loving goblins. So what happened is people started discovering that while they prompted sometimes ChatGPT, sometimes they would get goblins. So this guy, for instance, this user actually reported that it tested ChatGPT to draw a unicorn, and it actually drew a goblin. And there is actually many, many more things. And the things that is happening behind that is that actually, this was shoving goblins everywhere, and actually OpenAI had to intervene and actually patch ChatGPT so that it didn't do that. And the reason was, well, actually, ChatGPT, how it had several different personalities, which were defaulted by OpenAI. One of them was the nerdy personality, which is a personality when you're doing things that involve technology or science or, board games and chess and stuff like that, things that are usually associated with geek culture. These things, for these specific things, it has its own personality, and for that personality, ChatGPT actually, since it was people who actually helped code it, the people who coded, they themselves had a predilection for goblins, and hence they let it leak through the system. So a human kind of bias made the system have a bias, and this bias kind of got amplified by the training data of OpenAI. And the model is that, well, these things, these models actually have biases that we never asked for. We never even knew that they were there, but they might be there. We might be actually, days from actually finding the next one. And if we just start using ChatGPT right now, we're going to see that it has a bias to telling you that you're correct, that you're the best, most brilliant person of all times. Sometimes it might be correct, sometimes it might be wrong, right? And this is actually funny. So this example is funny, but this is exactly the kind of bias you cannot have inside of mathematical proof. And again, there's also another funny fact. I think this also became very viral, which is people asked, well, is there a seahorse emoji a while back? And if you wanted your ChatGPT to be thrown into a loop, an endless loop, and never go out of that, that was the perfect recipe. It would spit something out just like what's on the screen. It would say, would just like swear to you there is a seahorse emoji, and it would try every kind of maritime animal emoji ever, and then until it realizes that these are not seahorse emojis, and then he's tried like horse-related, unicorn-related ones, and then it goes on a loop, right? But it could absolutely not deny that there is a seahorse emoji. So it swears, it goes on a loop, and then when at a certain point it finally says, okay, I'm done, but it doesn't contradict itself. And actually it has a different cause from the goblins. And the cause is, there's this Mandela effect. There's many people who believe that Nelson Mandela actually died in prison in the 90s. And maybe some of us here at this talk will also react to this, to me saying this, like, wait, didn't he? But I think many people have this kind of false memory that Mandela died in the 90s in prison. So there's this terminology for when you swear something happened when it was actually something different, which is the Mandela effect. And there's a community of people online, on Reddit and other forums of such kind, that actually swear there was once a seahorse emoji, although there was never a seahorse emoji. And they go on and they go with conspiracy theories and telling conspiracy theories to one another about the seahorse emojis, but it doesn't exist. But then what happened is, since ChatGPT is trained on the whole of the internet, it was trained at some point on excerpts of things that actually swore that there was a seahorse emoji. So it got kind of used to believing that there is a seahorse emoji, and it got kind of like this extreme confidence in its existence, right? So you get out of something that is super naive, super harmless, like, some people experiencing Mandela effect, kind of a maximum confidence mistake, which is critical for us, right? So yeah, so we have seen so far, how these things can actually be good, how these things can actually be bad, but it's undeniable that in the past 2 years, these models have been starting to be actually very capable of doing math. So for Olympiad kind of math, it has non-trivial performance nowadays. You give it some Olympiad problems, the best versions of those models, they actually do pretty reasonably. Sometimes they're also thrown in a loop, but many of the problems they can solve, like half of the problems that the IMO, which is already a worthwhile display. And you can actually use it. So as far as I'm concerned, I have been starting to experiment with using these models as, assistants to my daily research for the past months. They can actually help us suggest lemmas, complete computations, complete proof of lemmas, propose counterexamples, map the literature. It has been kind of accelerating research for us. And of course, you can actually use it to iterate it with different tools, such as Lean, that I'm going to be talking to you guys about that. And this was all fiction in like 4 years ago. The last World Cup, right? Last time the World Cup happened, if people told you, well, in 3.5 years, not even 4, Germany and the Netherlands are going to be out before the round of 16, and ChatGPT is going to be proving theorems. You're going to be like, come on, what am I, a joke to you? And what is even ChatGPT, you would ask. And here we are, and we're living exactly in that reality that Germany and the Netherlands won't play the rest of the World Cup, and LLMs can prove some theorems, can help us prove theorems. And so the question right now is not, does it work? It works with some limited scope, but it works. But the question is, how does it change our job, right? What will we do? How will we go forward from that point on? And that's kind of the more philosophical part of the talk that I would like to focus. So in order to do that, I have to talk to you guys a bit about Lean. So what is Lean? Lean is a programming language that serves as a proof assistant. And what do I mean by that? So it is a programming language. So its elements, whatever you write in Lean, it's a computer program, and it's based on type theory. So every object has a type, and many things you actually have to build up based on types. Propositions are types, proofs are terms of types, and so on. So it's a bit complicated. It has to do with logic, but it's a computer program. It's a computer language, programming language. And the key of that, we don't need to go too deep into that because Lean is complicated, and learning it in depth is like learning a programming language in depth. It takes time. What we need to know is that, well, if you're writing a theorem in Lean, it is true if and only if the program associated to it compiles without warnings, right? So that is what Lean does. Lean is a programming language that encodes mathematics, and you get to prove theorems, and they're correct if and only if they're compiled by the kernel. And related to Lean, there's mathlib, which is the library with 1.5 million lines, which covers several areas of mathematics, and there are several different people that are working on this, such as like mathematicians such as Peter Schulze, Terry Tao, Tim Gowers. So this is a collaborative effort across the world, and it's kind of in the beginning-ish of its own of its trajectory, but that's what it is. It's a way for us to formalize mathematics, and I think all of us here see the immediate benefits of these things, right? So we always struggled with refereeing papers because sometimes we see like this computation, which is super messy, and we have to open it up and we have to check line by line whether that is true. Well, if the paper came with a program associated to it that says, look, my theorem is automatically true because there is this program that if you run on your own machine independently, it's going to tell you it's true. Well, then half of the work of being a referee is done. So our work is basically saying, well, maybe things could be reordered to be a bit better, or maybe this is not at the level of that journal and so on. But the part of verifying whether results are true or not, this could be a gone from our daily lives, which, as far as I'm concerned, again, I think would be incredibly valuable. We would gain a lot of time, at least from my perspective. So there is at least this, but there are several other motivations for this, and we're going to see a little bit of them a bit further down in a couple of slides. So let me give you an example of what a theorem in Lean 4 looks like. So we import mathlib. So we import parts of mathlib, and we want to prove that for every natural number, n plus 0 equals n, right? So a trivial theorem. So we call it a theorem. So as mentioned here, it's a theorem. We're going to call it add 0. It's its name. Here we're saying that n is a natural number, and here the property is that n plus 0 equals n. And after this is exactly just says that what we're using to prove this is RFL. And RFL is just reflexivity law of natural numbers. So A equals A, right? So this follows. And then a typical prototypical theorem in Lean looks exactly like that. We have to declare exactly everything we're using. We have to declare all the objects, and we have to say what the proof actually entails in, right? If the kernel accepts it, if we run this program and it compiles without warnings, then this is proved. We're done, and this is true. And if you run, of course, this very simple program on Lean, you're going to see that this is actually true. And the goal, so I told you before that Lean has this very nice application to making our jobs as referees easier, but maybe the nicest kind of tactic here is maybe try to get Lean to be incorporated into LLMs. And how? What is the idea? The idea is, well, we prove a theorem. We work very hard. We prove a theorem, and we verify it by hand. So we write it down. We write a proof rigorously, and we type it on the computer. We write it in the language of Lean, which is, trust me, way harder than writing a mathematical paper. But we go through this effort, and we have absolute certainty that our result holds. From that point on, the idea is to polish all the pieces that we used to construct the program of this result to the mathlib, to this library, so that if people need to use those pieces in the future, they can directly call it and they don't have to write it by hand, so future proofs become easier. And if we're trying to use LLMs, that I told you before, LLMs are fallible. They make mistakes. But if they have Lean running in the background to try to verify their ideas, then they have much more to build on, right? So they have much, much better things to kind of much better paths to try. And they can suggest more paths to proving things. And since we're done with that, then we get to back to step one. With the help of an LLM, we get more tools available, we prove better theorems, and we iterate, right? And so, the reason why this is of interest to us right now is that the more this MathLib library grows, the more we can actually have agents, have LLMs, have ChatGPT, have Claude, and so on, work on similar concepts and try to compose them to existing proofs. We can get them to search the library for similar stuff. And, and the idea is that in the future, maybe after we contributed it, maybe in 3 or 4 years, then the LLMs will be able to train on this data and get a bit better searching proof techniques, and they will be better even at helping us do research, right? So let me maybe give you guys some examples because, up until this point, you might be asking yourselves whether this is all fiction. And I tell you guys that this is already not fiction. So let me talk to you about a problem that I have been working on, and there is where analysis comes into play for us, which is, well, let me tell you about the problem of phase retrieval. So the problem of phase retrieval is, so let me say you give me the values of the modulus of a Fourier transform of a function, and you tell me to recover f modulo trivial symmetries. I need to make sense of several different things. So what are the trivial symmetries of this? Well, there are several of them. One of them is, well, multiplying by a phase, right? So that's why it's called phase retrieval, but also conjugating and taking like minus the argument is also preserves this, and several other, basic symmetries actually work. And actually, in nature, for instance, when you're working with optics problems, actually, I think in microscopy that is particularly relevant, and also in X-ray imaging, sometimes what you get as an image is actually the modulus, the magnitude of the Fourier transform of whatever you're trying to see. So this problem is super helpful in several different areas, from physics to medicine. And we have to recover the original function because we want to see an object in the real world. We don't want to see the magnitude of its Fourier transform, right? So the question that we have is, how does that determine the phase? How does that determine the original object? And how do we reconstruct it? Can we find algorithms for that? And as I said, this is related to medicine, to physics, and to also engineering. So X-ray crystallography is a physical example of that. Quantum optics, quantum mechanics as well. So this was, by the way, a problem proposed by Pauli in the 30s. Engineering and signal processing, this is particularly relevant. And medicine in imaging, this is in MRI modalities as well. This is actually particularly important. And now all that we're going to want, and more generally than the Fourier transform, is we have a signal f. We apply an operator a to f. We get a of f. We take absolute value of this, and we want to recover f modulo some symmetries, right? So this is kind of the basic setup. So as I said, Pauli actually posed this problem for the Fourier transform of a function in the 30s. And then Akutovich actually answers that for entire functions, this actually holds. If the function is complex and the whole complex, it's analytic in the whole complex plane, you can recover it. There is actually in the applied side several different algorithms telling us that you can get to recover the object from iterating it. More recently, there's been this whole theory. There's this boom of theory of phase retrieval frames, uniqueness and stability, also like related to random matrix theory. Also, the work of Candes is particularly important in that regard. And more recently, we have been working on sharp stability and rigidity. So what happens about, what is the rate of reconstruction? When can you actually recover the things? And so on. So we're going to be talking about two problems of phase retrieval type today. So the first one is of probabilistic flavor. And it's the following. We're going to have an x. X is a random variable, which is a linear combination of independent random variables. And we want to know when the modulus of x determines x up to a sign, right? So it's a real random variable, right? And we want to know when its modulus determines it. And the second one, it's a similar question, but for analytic functions that we already mentioned, right? So suppose we are in what we call the Bergman-Fock space, which is the space of analytic functions which integrate against the Gaussian measure on the plane. Don't worry, we're going to be talking a bit about that in the next slides. And when can we actually determine the function from its modulus up to a phase? And of course, our focus is going to be particularly on the constant function. So when can we, so coming back to this question that I posed in the beginning, we know that on an open connected set, if a modulus of an analytic function is constant, then the function itself is constant. When can we actually come up with the stability version of that? So if the modulus of an analytic function is very close to being constant, how much of it can we actually say that the function is constant, right? So these are the two problems that we're going to be working on. They have been posed by people in different fields of mathematics independently in both probability and complex analysis. But then these are the two questions we're going to be interested in today. And they actually use completely different methods, and our interest is going to be on what part of LLMs actually benefited both of them. So let's go for the probabilistic theorem first. Well, we say that we take, as I said, several independent random variables. They have L2 norm 1, and they have integral 0, right? So they have variance 1 and expected value 0 in probabilistic lingo. And we take a guy which is in the closed L2 span of those guys. Okay. And our problem is recover x up to a sign in a stable form from its modulus. Or, in other words, we want the minimum of the distance from x to y up to a sign to be controlled by the distance of their modulus. And the question is, when can we do that, and under which hypotheses on the variables psi I? And the theorem that we were able to prove is the following one. So take this random variable, so they're eta, xi2, xi3, and so on, and suppose that all of them except for eta, they have the property that their L1 norm is bounded from above by something strictly less than 1 and from below by something strictly larger than 0. So you can maybe think of that as this random variable is not concentrated at either 1 or at infinity. It kind of spreads its mass a little bit, and all of them have to spread mass in a kind of uniform way away from 1 and infinity. But we allow one of them not to do that. One of them could do anything as long as it has an L2 norm 1 and expected value 0. Under those conditions, then we can get the stable recovery that I was telling you guys about. And this is actually this is a sharp result. So the hypotheses in the psi I are sharp. If we remove the fact that even one extra of these entries of this psi I satisfies this two-sided bound, then the result fails. Why? Because then we can actually construct sequences that are approaching one another in absolute value, but the variables are independent, for instance. Hence, their L2 norm of their difference has to be 0, right? So this is a sharp result, and we were very happy when we were able to obtain that. So let me tell you a bit about the idea of proof. The idea is that basically we can reduce everything to orthogonal pairs. So there is this magic of phase retrieval that if you are trying to prove a phase retrieval problem like that, there is a result that allows us to just reduce to whenever everything is orthogonal. So we do that, we suppose x and y are orthogonal, and we suppose that the result doesn't hold, so that we can get a contradiction by taking some sequences that are bounded in L2. And then what we're going to do is like this very specific idea in analysis that, well, suppose something doesn't hold, maybe we can get some compactness, maybe we can get some sort of almost compactness of these sequences. And what we get is exactly that. We decompose our sequences into two parts. One of them is what's called the head of the sequence. which is converging to a different random variable, and one of them is the tail. And basically what we say is like, look, if the tails have no mass, then everything is good, because we're just like basically contradicting phase retrieval. If they do have mass, we get an equation like this that's on the screen. We got Rx and Ry. It's an infinitely divisible vector, which is a vector of random variables that can be written as as many sums of independent, identically distributed variables, vectors as we want. But then the thing is that, so what, at the end of the day, by using this condition with this infinite divisibility, we get that this vector Rx, Ry has to be concentrated on a cross. And then the lemma that crucially kills everything is that if it's concentrated on a cross, it's concentrated on a line. If it's concentrated on a line, then one of them is a multiple of the other, and then everything falls, right? And then we can get a quantitative version of this. So this is basically the idea. It's a very probabilistic result. But I think more important, even nicer than the result itself is how did LLMs help us prove it, right? So first of all, what we have about this result is that actually LLMs helped us formalize it in lean. So this result is fully formalized in lean. So it's proof. It's not only that the statement or result of the result, which is written to you right before your eyes in lean. So this is how our result looks. So here you may see several of the artifacts that we had. We have a natural number. We have xi random variables. So their average is 0. Their L2 norm is 1. You have 2 constants that bound the L1 norm from above and below. And here is basically the statement of the result. So you can see that the basic elements are there. But the result is proved in lean. So that means that whenever we are, so this is about to go out, I think maybe in a week or so, this is going on archive. But what really concerns us is that whenever we're submitting this paper, the referee doesn't have to check a line. It just has to run a program on the computer, and that's it. And yeah, so this is the first way. So LLMs actually were vital in doing that. Without LLMs, we're not going to be able to formalize this result. But other than that, it also in getting the ideas, they were quite crucial. So the starting point was we had a proof of the LP case for p greater than 2, right? So in a non-sharp case, we had a proof. And then GPT, we actually did a literature search, and it found arguments that helped us prove the L2 case. But then GPT actually proposed a different kind of idea, which was like it kind of understood, well, didn't understand anything because these things don't understand. They don't have a concept of understanding. But it kind of, suggested to us, well, maybe there is an underlying principle behind. And, well, and it was right. And we actually got the proof that I told you guys about through a suggestion of ChatGPT, and of course the ideas were ours. And in the end, we actually made the result quantitative, removed the contradiction step by just using some sort of combinatorial strategy and uniform estimates that ChatGPT, we were guiding the LLM, and ChatGPT actually was able to help us. Or it didn't help, well, it actually hallucinated a lot, right? So we try to get it, like, for instance, in this part where we said it suggested as a direction, we try to get it to implement this direction. It absolutely couldn't. It would be hitting a brick wall all the time and would be saying that this was not possible when we knew it was. It generated lean. So in the part of formalizing this in lean, it generated code that was very low quality. It had to be rewritten. It had to be checked multiple times over by us. It had to be iterated by us. So the bottom line is that it really helped us do some non-trivial mathematics. And because it suggested this lemma that's on the screen. It suggested that if an infinitely divisible vector is supported on a cross, then it's supported in one of the lines, right? And we came up with the rest. Okay, so let's talk about the other problem, the more analytic problem. right? So the analytic problem, it starts with the function that is on the Fock space. So the Fock space is just analytic functions on C, which integrate against this weight. So there are basically functions which grow less than exponential of z squared. You can think of them that way, right? So if you expand them in power series, then they have this property that the norm, if you define the norm like this, and the norm is just this sum. And the idea is, well, we want to recover f up to a phase near the constant function, right? And it is a different mechanism. Before we had randomness, and randomness was kind of like you generate noise, and noise is actually preventing things from, failing this phase retrieval property. Whereas here we have analyticity, which is the opposite of noise. Things are so smooth that you should also be preventing things from failing phase retrieval. And our result is, well, it's a bit simpler than the previous one. It is exactly that. If we want, we can actually, it's kind of like, you can think of it as a reverse triangle inequality. We can bound the distance of a function like that from constants by the difference of the function, the modulus of the function and the constant one, right? So it's basically saying we can reverse the triangle inequality, or we can recover, we can say that a function is quantifiably close to a constant as long as its modulus is quantifiably close to another constant and the exponents are sharp, right? Right, so what does the proof look like? The proof is basically, again, we do some sort of orthogonal reduction, and we use some sort of like local stability of our results. So it's suffices to prove things locally. And then we decompose the plane into like polar, like spherical shells. And what we do is like at very far from the origin, only some of these coefficients here contribute to one of those shells. The other ones are going to be very small. They're going to contribute to a very low factor when you take this Gaussian into account. So what we do is do a polar decomposition, then this basically makes all of these modes, all of these powers in the power series decouple. So we can actually get estimates on these circles, which are sharp and uniform, and we can actually use it to localize everything, and then to sum everything up, we just put everything together. So basically that's the mechanism. The mechanism is all of the observation that by looking into polar coordinates, we can use some sort of orthogonality, disjointness of support. It's not exactly that, but that's the idea. And again, this result is also lean verified. You can see like the basic stepping stones of that result right here, right? So this is, we see again that here we're defining the Gaussian measure. So it's a measure, and we're taking the volume measure. We're taking like some constants here, and we're taking the exponential and so on. So we're defining the Gaussian measure here in the first part, and then we're taking the theorem. Basically what we say is like, yeah, we had some sort of, so this is the more general version of the theorem. You can take P to be, I don't know, PZ to be just basically 1. And this is basically just saying that, well, the distance of a constant, a complex constant times our function to 1 in this Fock norm is bounded by the distance of their moduli in the same norm, right? So it's a bit clumsy, but if we take a close look, we're going to be able to see that this is the same result written in a different language. And this is stated explicitly. And we have to, of course, tweak a little bit of notation because otherwise things would not compile in Lean. Okay, but how did the LLMs help us then in this thing? It tried to solve the problem, right? So we prompted it to solve the problem, and it really tried. It claimed that it could solve the problem, but it didn't. It said, oh yeah, you just do this with this kind of idea, and it should be done. And it was very wrong. But it unlocked a kind of idea that is very common in physics. And in hindsight, we should have been able to see that. But we were able to discover this idea again through the help of LLMs and actually refine the estimate. So we had a loss of a log. And then by iterating with ChatGPT or its coding version called Codex, we were able to refine it and get the full proof. So the key reduction So this basically your orthogonal reduction, this polar coordinate, this did not come from an LLM. So this was an idea that we had based on a conversation with an LLM, based on a wrong idea an LLM had. And in Lean, again, the same mistakes were made. It had caused several problems, had to be checked, and had to be basically babysitted again. But it helped us a lot. And the anecdote here is that through an incorrect suggestion, we got the result. Right? So through an incorrect suggestion of something that was kind of available in the literature, we got a different idea, and this gave us a result. And of course, the LLM helped us prove the result in Lean. So let's maybe talk about this autonomous verification part in Lean, right, that I was talking to you about. So basically, the pipeline is like this. So how we have been doing this is, well, we write a proof in LaTeX. Then from the LaTeX, we try to get the LLMs. So ChatGPT, for instance, we try to get ChatGPT to write a Lean statement of the result. Then from that, we prompt the LLM to look back at our proof and to create a skeleton of how it should look in Lean. And then we go through a search. We go through a search of what of those parts of our proof have been proved and what not. And then we iterate. If we hit something that has not been proved in the math library, in MathLib, then we go back and we try to get it to work. And once we get it to work, once we iterate it long enough, it gets to prove all the lemmas that we want. And once it proves all the lemmas that we want, then there is no fail in the iteration of the program. Then the kernel checks, the program runs without warnings. Then, the next step to us is let's refine what we proved, let's contribute to the math library, and let's run everything again. So this is how basically we're envisioning things, and we were doing things so far. And basically, what we were doing is we were dispatching several agents to work on several different parts of the things, and every step is checked by the kernel so that no hallucination survives. Okay, so what is the step-by-step part of our program? So first, we want to break our program into self-contained pieces. We extract all of these external references, we extract all of the common mathematics, and differentiate it from the cited results. We isolate the lemmas that are already in MathLib. We isolate it from other lemmas that might be available, and we review it for correctness. And then we make a blueprint. And what is that blueprint? We make a file that actually wants us to say, look, we need to prove this, and that, and we need to go in order. So we go for that in order with all the hypotheses explicit, and we need to check whether the results exist, and we iterate, right? So then after we have this Lean, we have this outline, we have this blueprint, what we do is we checked whether results exist in MathLib or not. We are absolutely sure of what has been proved and what not. Then what has not been proved, we go and we dispatch an agent. We just dispatch basically a version of ChatGPT to work on that. And we dispatch several of them in parallel. And what we sometimes I think to formalize a simple result, I had once to dispatch maybe 10 agents in parallel. And of course, we get them to work independently of one another. They don't change the part of the pipeline that the other agent is working on without actually flagging it. And what we do is at the end of the day, we try to get everything to be sorry-free. So sorries are basically what people insert in Lean when they're lazy to prove something, and axioms are basically assumptions that people prove when they're lazy enough not to prove something. And we get these, so the LLMs actually produce these as well, because it turns out LLMs are also lazy. But you can get it to be sorry-free. And at the end of the day, we get everything to be running smoothly, and we annotate everything, and we polish everything, we contribute to math library. So this goes back, LLMs get trained on those, and next proofs get easier. Okay, so it all sounds very good, but what is the catch? And the catch is, well, it takes basically a long time to get these things formalized. So recently I had a counterexample, wanted to formalize in Lean, and it took agents 2 days to formalize it end to end. It was not running all the time, but it needed my attention, and sometimes it was running for 2-3 hours straight, and still it took a long time. And of course, this costs a lot because it consumes the usage of these LLM models by a ton. So this is not cheap, like money-wise or token-wise or however you want to quantify it. And of course, you need to iterate things. You need to be a babysitter, right? So you need to be and saying, look, no, your axioms are not good, stories are not good, and you need to go and iterate the pipeline. And of course, we want to refine everything. We want to make everything super explicit so that there is no hidden catch, no hidden assumption. And of course, as we're saying, this doesn't work without human intervention. We had the crucial human intervention it had to be there, otherwise this wouldn't have run. But the bottom line is it's slow and expensive today, but we get absolute certainty, and in the future, it's going to be helpful to us. Okay, so what did the agent do well in terms of LLM formalizing? It found lemmas, it resolved glitches, it learned to structure blocks, but then it also invented lemmas that didn't exist and mixed this Lean 4, which is the one we're talking about, with the previous version, which is, nonsensical. It lost track of what was being proved. And it failed at global reasoning. We needed, of course, humans to intervene, right? So there is pros and cons, just like anything. But then what really I think like the deeper message here is so this is very useful as long as we know what to ask for and how to do it. And what is the perspective for the future based on that? And for the short and medium term, I think we're all going to be profiting a lot from this co-pilot, right? So we're going to be proving fewer and fewer of these boring lemmas and doing boring computations. And maybe, within a couple of years' time, it's going to have become more or less common. Let's not say the majority, but let's say a good deal of mathematicians in some years will be trying to formalize their results in Lean in parallel with writing. And we can verify computations, we can search for lemmas, we can search in literature much easier. But in the long term, we don't know, right? And that's all we can claim. And my stronger claim is anyone who tells you anything about this, optimistic, pessimistic, or anything, this is just guessing. I have a particular good feeling about this. I don't think it is apocalyptic as some people suggest, but this is a feeling. But what doesn't change, and about that I'm very confident, is that the ones who actually assign meaning, beauty, connect philosophically ideas, and decide what is worth asking are humans. And LLMs will always be nice tools, but mathematical work and mathematical thought is a human endeavor. Right, so for the future, well, we want to make to contribute to phase retrieval these lemmas that we produce to the MathLib. We want the autoformalization benchmarks to be contributed and to be more ubiquitous in harmonic analysis. And in terms of LLMs, we want to improve this pipeline that we told you about. We want to improve the agent-assisted proof search. And, we want to bring the results, maybe to mix them back, going back to the mathematical part of the talk, to experimental phase retrieval. And, I think that's a good place to stop. Let me leave you with a recent thought of Terry Tubb, who said that, well, he thinks that this new wave of technology is going to be very transformative for math, and that mathematicians and AI will work together. So with that, I thank you guys very much for the attention.
Okay, nice talk. Very nice. Let me open for the audience question or comments. Very nice this. So the audience can just ask question for João or write in the chat and questions or comments.
I do have a question.
Okay, Gabriel, go ahead.
Thanks, João, for the presentation. It's very interesting. I just want to know if you have tried the approach of ending a party. What I think in this situation would be like you write the theorem in lane and let the agent run until it found a solution.
Yeah, we did, and it failed kind of miserably. We needed to. Yeah.
Go ahead, please.
No, yeah. Just gonna say that we tried it. We just like, look. We said that this is the statement that we have. We need to prove this in lane. Can you try to find the way to prove it from, like, maybe if we even gave you, I think we even gave it the paper. We even gave it the paper, right? So that it could iterate based on that. But it didn't. So it kind of like came back with just very raw things and very, like, several different axioms, several different sorries, and so on. So in order to actually formalize everything, it was a bit more complicated than that. And I think, like, at the end, we would need still like a .md file, like an instruction file, telling exactly the LLMs what to do and how to break down the article in order to search it. But we did try. We tried several things. What worked was basically this pipeline that I told you about, like break everything, create blueprint, and then deploy agents.
Yeah. And do you have a problem, because I played with before, but having get problems again and again, which was like the ChatGPT just gave up. I can't do that. Instead of just blowing up the context. Do you have this problem?
Yeah, that happens a lot. I mean, that happens in both stages as well, right? It happens when just like ChatGPT says, "Oh, this is too difficult." And then sometimes you think it's like you have an intuition and you say, no, it's not, try to do this and that. And then it kind of magically can do it. And some other times, even when trying to verify something in Lean, it says, oh, this is too much of a task, I cannot do it. And then when you break it down for it and you study exactly what to do, it does it. So I think the best way I can describe it is, well, don't take it the wrong way. I'm not offending master students by it, but I think this is a very, very good. It's like you had a master student that knows all of mathematics. That's what ChatGPT is equivalent to, basically. It can get to the same kind of logical conclusions as master students, but if you don't break it down super, super neatly so that it can verify it, just basic building blocks, it won't. But yeah, I think everybody kind of has this problem. But it's a very good question, because we have to talk about also the roadblocks, right? And this is one of them. These LLMs, they're lazy, so they sometimes it's like, oh no, I can do it. This is too hard, and you're like, no man, just try something else, and it magically does.
Yeah. Okay. Thank you.
Yeah. Thank you for your question.
Okay, thank you very much. We have time for another question or comments. Okay, in the chat. Okay, no question, no comments. Thank you, João. Very, very good, nice talk. And, thank you to participate in today with us. Okay, thank you very much.
It has been a pleasure. Yeah, thank you very much, guys.